Welcome. Welcome to third video in a series of videos that I've created for you to self-evaluate yourself relative to a number of skills that you need in order to be able to perform well in mechanical engineering classes. What does that perform well mean? Well, on the short term, it means to get a good grade in your class. Beyond that, in the longer term, perform well means that you're going to be preparing yourself to become a practicing engineer. This particular video has to do with your self-evaluating your ability to perform integrals. So let's get started and see how you're doing. Very important skill that you're going to need is integration. And so our expectations of you in mechanical engineering are that you need to be able to do three things relative to integrals. You need to be able to visualize, understand what you're doing, and then numerically perform basic integrals. I have a number of examples that I'd like to go through from easy to relatively complex. So this is going to give you a chance to see sort of where you stand and where you might need to improve somewhat. Let's look at your basic understanding of integration. I was first exposed to integrals when I was in high school. My last year of high school is when integration was introduced to me. So let's recall simply the visualization of any integral. So let's say you're given a function, y equals f of x. Here on this graph, y versus x, I've shown it as a squiggly line, so it can be any function, okay? The integral of that function, the integral of f of x dx, going from x1 to x2, visualization is the area under the curve. And I became kind of comfortable with that. So I was not comfortable with integration until my high school teacher said, let's start thinking of this as an area under the curve. Can you visualize the area under the curve? And then I started getting more comfortable with what integration was all about. Another thing that's important in understanding integration of functions is that for any function, I've drawn in two sort of squiggly functions. When x1 is less than x2, you're integrating from left to right. And so that area under the curve is visualized to be positive, integrating from left to right. The integral value is going to be some number bigger than 0. And you can kind of see what that number will be by looking at that area. Now, in a situation, let's look at the other situation where x1 is bigger than x2. You're going from right to left, okay? Now, the same thing applies in terms of looking at the area under the curve. So I think I can sort of visually see this area under the curve. However, the numerical result is going to be a negative number because you're integrating from right to left. Now, I know there are lots of fancy mathematical derivations and proofs to show this result. But look, when we all went through the class, I think we all generated sort of a common sense understanding that, let's review, when we're integrating left to right, we're going to get a positive numerical result for the integral. When we're integrating from right to left, although we can see the size of the integral, it's going to be a negative value. So this area under the curve concept applies to both directions. All right, so let's start with an example problem of integrating a very easy function, y equals a constant, y equals constant. What will that look like on y versus x axes, y equals constant? It's going to be a horizontal line. Okay, so area under the curve. Remember that for these integrals, so let's let little w be the integral value of our function y equals c. Okay, so our function, very simple, y equals c. So w is the integral of y dx, or in other words, for this one, y is the integral of c dx evaluated from 1 to 2. So one thing I didn't do well, oh, I see what I missed on my slide. This x1 and x2 needs to also be shown up here on my integral, okay? And so sorry about that. But now let's perform the integral. Well, I can pull a constant out of the integral, so all I have to do is integrate the integral of dx. Well, that's just x, right? So next step, w is equal to c, the constant, times x evaluated from x1 to x2, okay? Or c times the quantity x2 minus x1. So that's going to be some number bigger than 0. All right, and then here's our visualization. I probably should have started with that, shouldn't I? Our visualization of the integral is the area under the curve, or the area of a rectangle. And here we went through the math first, and that totally agrees with the visualization. Okay, so the important takeaway from engineering: you can perform the integral, evaluate the value of the integral using the stated limits, x1 to x2, okay? And that perfectly agrees with our visualization of the area under the curve. Okay, well, shame on me for not putting in x1 and x2 on my slide. All right, now let's do another integral. Let's do one where we plot x equals constant. X equals constant. What does y versus x look like for x equals constant? That's a vertical line. Okay, so let's visualize little w, the integral for a vertical line. All right, so this time let's go and look at our graph first, okay? What's the area under the curve of this vertical line? It's 0. There's no area under a straight vertical line, is it? Okay, that's a neat observation. So for the function x equals constant, the integral of y dx is 0. Okay, and so there's our big conclusion for this, is that there's no area under the curve. So similarly, let's look at the math a little bit. X equals c. And so therefore dx, the incremental change in x, dx, incremental change in x, is 0. So the integral of y dx is 0. So the math totally agrees with our visual look of the area under the curve. Okay, so we've been to two examples: a horizontal line, the integral of a horizontal line from x1 to x2. We just went through a vertical line from x1 to x2. Next level of difficulty, a linear relationship, y equals mx plus b. Straight linear line. That reminds me of the previous video where you said, well, I feel very comfortable with a linear relationship. Well, now we're going to look at integrating that relationship. Okay, and so here's our y equals mx plus b, the familiar y-intercept right here. And what we want to do is we want to look at the integral of y dx, the integral of mx plus b dx. Well, let's use our area under the curve method first. So before we do the math, let's do our area under the curve and see what we come up with. All right, so we draw in our y versus x. Here's our starting x1, finishing x2. Wow, I can visualize the integral of y dx with the area under the curve. This is a trapezoid, isn't it? That's a trapezoid. And so it's a little more complex than a rectangle, but not by much, okay? Here's the width. The width is going to be x2 minus x1. What height would we use for a trapezoid? We would use the average between y2 and y1, so the midpoint between those two, to kind of make it a equivalent of a rectangle. That would be the height, the average of y1 and y2. So sort of almost by inspection, w, the integral of mx plus b dx is going to be the width, x2 minus x1, times the average height, y2 minus y1 over 2. And boom. And so if you have all those numbers, put them in calculator, boom, you have numerically the integral of y dx. Not so bad. Now, let's go with method 2. Okay. Let's do the math. So we could pretend like we're not familiar with this area under the curve concept. So let's just do the mathematics. W, the integral, is equal to the integral of mx plus b quantity dx, evaluated from x1 to x2. All right, now, so what I'll do to continue with my math, I see that I've got two terms. I've got to do two integrals. I've got to integrate mx dx plus the integral of b dx, both from x1 to x2. All right, so I'll do both of those integrals. Let's see, m I can pull out of the integral, so I've got to integrate x dx, back to high school. Let's see, the integral of x dx, I'm going to increase the exponent 1, okay? So it's going to be x to the 2, but then I've got to divide that by 1 plus 1, okay? So I've got m over 2, x squared, right out of high school, okay? Second integral, the integral of b dx. Now that one's easy. B is a constant. I'll pull it out of the integral. All I have to do is integrate dx. That's just x, evaluated from x1 to x2. Okay, so there's my next step. Now I'm going to do the math. And so I've got, so my first term, m over 2 times quantity x2 squared minus x1 squared, evaluating between the limits, plus the second term, b, evaluate x from the limits x2 minus x1, and there's going to be my result. Okay, so that's doing the math. So let's recap. Let's recap this basic linear relationship, integrating it. Method 1, area under the curve. We visually saw, okay, we wrote it down, x2 minus x1 times quantity y2 minus y1 over 2. We got a different result for the math. However, if you do some thinking, you're going to see that these are exactly identical. These are identical statements simply because of the linear math. Okay, so for this particular situation, either method will work. It's just a matter of what's easiest for you and what data that you're given. Okay, if you're given the x's and the y's, go with method 1. If you do not have the y values and you only have the x values, go with method 2. Okay. Next example, a little more complicated. We need to integrate a hyperbolic relationship, that hyperbola, y equals a over x. If this looks not familiar to you, go back a video and look at the plotting of y equals a over x. It's a hyperbola. All right, so I've drawn it. So here, if you're doing a homework problem, this is fine for you to draw a hyperbola with pencil and paper, okay, so that we can come up with a numerical result. I've done this in Excel also. I've plotted y equals a over x, where a is 2.5, and we're trying to do the integral. For our example, let's go from x equals 0.25 up to x2 equals 1.25. So I've shown those on my graph, and now with our eyes, we want to integrate from 0.25 to 1.25 of y equals 2.5 divided by x. So with my eyes, I can see a positive integral, see the area under the curve, but getting the area under the curve is not going to be quite so easy this time, right? So we can't do it graphically. No, we're going to have to integrate this mathematically. All right, so let's do the integral. All right, so next step, y equals, or w is the integral of a x to the minus 1 dx. So be sure that you understand up here, y equals a divided by x. Down here, y equals a x to the minus 1. Those are identical statements. Okay, we've got to integrate. Okay, so let's take our time. Oh, I can't increase. This doesn't work the same way as y equals mx plus b, because I've got a minus 1 up here, and I can't add 1 to that. I've got to remember from high school that the integral of x to the minus 1 is the natural log of x. Now, I pulled a out of the integral. It's a constant, okay? So the integral of x to the minus 1 is the natural log of x evaluated from x1 to x2, okay? I hope that is familiar to you. Okay, I'm starting to remember that now. Okay, we're going to continue on with our algebra to flesh this out. We got to come up with a number for the integral of f of x dx from x1 to x2. So we're going to jam in a times natural log of x evaluated from x1 to x2 is a times the quantity natural log of x2 minus natural log of x1. We can simplify this because we got to minimize our calculator time. A, there's our constant. Now, the log of two differences, the difference between two logs is the natural log of the ratio of the two numbers. And so this is identical. A, natural log of x2 over x1. This makes our calculator work easier. Okay, and so now we just jam in A, okay, natural log of 1.25 over 0.25. That's just 5, natural log of 5. So now calculator work, natural log of 5 times 2.5 is 4.024, and we've got a numerical result. Make sense? You're going to be doing this over and over and over again in thermodynamics class. Okay, so now let's remember, similar to that graphics video, the plotting video, equivalent ways of expressing hyperbolic relationships. All these are equivalent. And one thing I want to point out to you that the most usually observed starting point in thermodynamic class is yx equals a. So that's a commonly observed way that hyperbolas are expressed, okay? And that's equivalent to y equals a x to the minus 1, okay? Now we're going to move on to the most complex example of needing to integrate, okay? And that's, both of these are equivalent statements. Y equals a divided by x to the k, where k is some number bigger than 1, some might be 1.1 or 1.2 or 1.3. Rarely will it be 2 or more. Okay, it's going to be 1 point something. Okay. This is identical to y equals ax to the minus k. Let's review how we would integrate this function. Okay. And so for our example, we want to look at the integral of ax to the minus k, okay, where a is 3.2 and k is 1.3. Okay, so I've plotted this in Excel. So I've plotted this formula function y equals a over x to the k, okay, and I want to integrate this. Well, let's see. Let me go back and see if oops, it doesn't look like I said in my problem statement what I want to integrate from. Well, shame on me. I want to integrate from 0.15, x1 is 0.15, and I want to integrate that up to x2 is equal to 0.45. So I didn't put that in the given, so sorry about that. All right. Well, oh, here it is. Here it is. I missed it. We want to integrate f of x from 0.15 up to x2 equals 0.45. There it was, staring me right in the face. Sorry about that. Well, this is a power curve. Your hand-drawn sketch will work, okay? And then you would shade in the area under the curve between 1 and 2 just like I've done in Excel here. So we have a visualization of the integral. We can't do it graphically because this is a curve. We can't integrate this graphically. We've got to do the math. Okay, so we're going to integrate w. That's going to be, we're going to call that the integral, is going to be a x to the minus k dx. Okay, so here we go. All right, so I'm setting it up. So I got confused there for a minute. So I think what I'm going to do is work down the slide. Okay, here's the setup. Here's our visualization of the integral. So we're going to try to go through the steps to integrate a. Oh, well, first step, I pulled a out of the integral. Pulled a out of the integral because it's a constant. All right. Now here we go. All right, so I've got x to the minus k dx. Now, how will I integrate that? Oh boy. Oh boy. I've got to add 1 to minus k and put that in the exponent. There it is. Okay. I've also got to divide my constant by minus k plus 1, or 1 minus k. Okay. I got to tell you, even at my advanced age, I have to write down in pencil and paper how to do this, because I find this impossible to do in my head. Okay. So don't be ashamed for you to write this down on pencil and paper. And here I'm writing down the limits. I start at x1 and end at x2. There's my visualization, the positive value. I'd better get a positive value for my integral. Next step. Next step, what did I do here? I evaluated x to the 1 minus k from x1 to x2. So I wrote that out. I continue. Here's my my constant value, a over quantity 1 minus k. Okay. So I evaluated the integral. What's the next thing I do? The next thing I do is I'm going to prepare for thermodynamics and recognize that k is some real number greater than 1, slightly greater than 1. So the next thing I'm going to do is simplify my mathematical expression. This will work. You could go right to your calculator with this. That could work. Go right to the calculator and you can put in the value for k, 1.3. You could put in the value for a, 3.2, and get a numerical result. But looking ahead, to minimize calculator work, what I'm going to do is switch. I'm going to switch it. Notice here the denominator 1 minus k. Down here, I flipped the sign SIGN of the denominator, k minus 1, and that's what enables me to flip the bracket term. Instead of x2 to the 1 minus k minus x1 to the 1 minus k, I've got x1 to the 1 minus k minus x2. So all I did was flip the sign SIGN down here, because k minus 1 is going to be some small number. Okay. It won't be a negative number that way. Next step. Okay. So in the bracket term, what I did was, and this is for me in my own calculator work. So I replaced x1 to the 1 minus k with 1 over x1 to the k minus 1, because k minus 1 is going to be some small number. And this simply helps keep me straight in my calculator work. So recognize that these aren't obvious next steps. These are next steps that I sort of taught myself to do when I was in thermodynamics class as a student and trying to minimize the work I was doing on my calculator. Okay, so that was a little rattled and a little awkward, but I think I got my point across that this power curve is difficult to integrate, no doubt about it. Okay, and so now, well, now we ended up with I hate to use the word formula, but we did the integral, but now we've got to jam in our numbers and go to calculator work. So here's a is 3.2, k is 1.3, x1 is 0.15, and x2 is 0.45. I've got 4 numbers and a lot of calculator work to do. I put those numbers in, and typically I write those down on pencil and paper before I go to the calculator. Go to the calculator and you get your result. The integral of the function from x1 to x2 is 1.221. This is sort of a start to finish, but complex example of the type of integration you will be doing in your thermodynamics class. Okay, so finally, expressing this power function in different ways. All I want to do here is point out that in thermodynamics class, the most usually observed starting point is this expression of the power curve. Y times x to the k is equal to a constant A. By far and away, when you're dealing with this power function, this is the format that you normally read it in. So, mental exercise now. For the function y times x to the k equals a, what will the result of the integral be when k is 0, when k is 1, and k is 3? Let's think about it. Just take a real quick minute to think about that. When k is 0, x to the 0 is equal to 1. So y equals a. Y equals a constant, horizontal line. What will be the result of the integral for a horizontal line? Y x to the 1 equals a. Y times x equals a. That's a hyperbola. What will the plot and then the integral look like on that? And then finally, when k is 1.3, what will the plot and then the integral look like for that? Okay, so when k is 0, when we integrate that function, it's the area of a rectangle. That's something you can do with your eyes. Don't have to do any fancy math. When k is 1, it's the area under the hyperbola. You've got to do the math, and then you remember that involves, for the hyperbola, that involves natural log. Can't remember the formula in my head, but I do remember it involves something with a natural log. Power curve, k is 1.3. Relatively difficult integral. You've got to do it on pencil and paper with some difficulty. Yes. Now let's look ahead towards thermo, because in thermodynamics class, we don't deal with y's and x's. Typically, we transform what we're familiar with from high school and college into the engineering world. And so y sort of translates into the variable P. Looking ahead, that's going to be pressure. And x translates into the variable little v. That turns out to be a variable called specific volume. Okay, but we have lots of mechanical engineering problems associated with these variables. So we graduate from x and y, and we end up working with variables p and v. So let's look at some examples of thermodynamic processes going from x1 to x2, okay, or v1 to v2. When p is constant, well, p is constant. That's like y is constant. That's a horizontal line. What will the integral be for a horizontal line? How about v is equal to a constant? That's like x being a constant. That's a vertical line. What will the integral be like? Integral area under the curve, 0. Right. PV equals constant. That's going to be a hyperbola. The integral will be something that involves natural logs. And then finally, PV to the K is constant. Well, that's a power curve. And that's going to be a pretty complicated integral that'll look like a steep version of a hyperbola, a complicated integral. Now, some friendly advice. Friendly advice for you is to try to avoid a formula mentality. So many students come in believing that mechanical engineering classes are going to be a study in the professor giving you a formula, and your job is to use your calculator to plug in numerical numbers for the given variables and you get a numerical result. That's not the way the mechanical engineering classes are going to work. So we don't give you formulas simply to evaluate numerically with your calculator. And so students, including myself when I was a student, the famous phrase was, what's the formula? What's the formula? All I can do is persuade you to try to avoid that. And my professors finally beat it into my head that I needed to get away from that formula mentality. So here's what we do. Here's what we do. Start with a Y versus X sketch. Hand-drawn sketch is going to work fine. You're going to have to integrate, okay, throughout your classes. So visualize the integral on your sketch. Visualize it, area under the curve, okay? Then perform the integral. In other words, do the math on pencil and paper. You come up with a mathematical expression that you derive, not formula, not given formula, okay? Then numerically, you're going to evaluate the integral with your calculator to get a numerical result. And then finally, to close it all up, does the numerical result you got make sense? In other words, is your visuals, are you integrating from left to right? Did you get a positive number? Are you integrating right to left? Did you get a negative number? If not, you got to go back and find out where you made the mistake. Okay. Friendly advice, avoid a formula mentality. I hope this made some sense. Some examples were easy. Some were tough. No getting around it. Some were tough. Okay. You will get better and better at this the more you practice. And I've said in a previous video, you're going to get plenty of practice at this in your mechanical engineering courses. Okay, now's the time for you to self-evaluate where you're at. Okay. Do you feel pretty good about all of those examples? Okay. If you do, I think that's great. You're ready to go. Do you need some memory refreshing on doing the mathematics of integration? Okay. Doing the mathematics of integrating a function. Well, if you need some brushing up, particularly on that hyperbolic, the natural log, oh yeah, I remember doing that, I need to brush up. Maybe you could go to the internet and get some either YouTube guidance or Khan Academy guidance or something like that on basic integration of those example problems I gave. Okay, that can work. If you said, this stuff, I don't even know what integral means. I'm not understanding what an integral is. I don't get it. I was never exposed to area under the curve. I never heard of that before. If some of this material that you heard on this video is brand new to you and you don't understand it, help is available. And I want to encourage you then, if you're in that situation where this is totally Greek to you, go to your undergraduate advisor. Set up a face-to-face meeting with your advisor, not just a Zoom call, but go and visit your undergraduate advisor and develop an action plan where you two can reach out to instructors in other departments, and your undergraduate advisor should be able to help you with this, or places within the university that can help you get up to speed mathematically before you begin your mechanical engineering classes, because instructors and professors operate our ME classes at such a fast pace that we don't have the opportunity to work with students one-on-one to get them up to speed with mathematics. And so, although we wish we could say, let's go all the way back to high school, or let's go all the way back to college math, and let's explain about integrating. The chances are very high that there's not going to be enough time to do that. And so we do have an expectation that you have the ability to visualize, to set up, visualize, and execute integrals on your own before you get into this engineering problem solving. So I hope that helps. So if you feel like this material is totally not understandable, quickly go to your undergraduate advisor. Help is available at Virginia Tech to help get you up to speed, but you must get up to speed. So we want you to perform well in your classes. We want you to be well prepared on the mathematics side in order to perform well, or in other words, get a good grade in your classes and prepare yourself to be a good practicing engineer. Wish you best of luck in your classes, and best of luck as you get improve your skills in mathematical execution.